Everyone, this is Professor Monty. Welcome to chapter 15. Now in chapter 15, we're only doing a single section. We're just doing 15.2, which has to do with inferences. Specifically, what we're going to be doing is we're going to do hypothesis tests on the slope of the population regression line. So we've talked about the regression line before. Now we're going to determine if statistically it's going to be useful to predict y given x. So the idea is performing a hypothesis test to see if the regression line is useful in using x to predict y. Okay, that's our whole idea. That's the thought for today. Now, recall the regression equation using the sample. We got y hat equals b sub 0 plus b sub 1x. There's my regression line. And again, that's just from the sample data. But what we're talking about, notice up in the title, it says inferences for the slope of the population regression line. So the population regression line we'll be more specific here, equation. Okay, so now it's the whole population. It's going to look similar to that y hat. It's not y hat anymore because it's not from the sample. And instead of using b sub 0, they're going to go back to what they usually do when it's using population data. They're going to use the Greek letters. Well, the Greek letter for b is beta, so they're going to call it beta sub 0 plus beta sub 1x. And again, beta sub 0 is going to be the y-intercept because it's constant. And beta sub 1 is going to be the slope because it's multiplied by the x. Okay, so here's the idea. If the slope beta sub 1 is equal to 0 or close to 0, the regression line is not useful. Oops. Let's see. Erase that. The regression line is not useful in predicting y with x. Well, here's why. So say I was equal to 0 for beta sub 1, I would look like this. But 0 times x is still just 0. So that just gives me y equals beta sub 0. Well, x isn't useful because x doesn't appear anymore in the equation. So if x isn't there, it can't be useful. So that's the idea. So if beta sub 1 is close to 0, that means x isn't really changing the value we're getting from y at all in the equation. So for our hypothesis test, what we're going to do, so hypothesis test, the null hypothesis is going to be that that beta sub 1 is equal to 0. That would mean the slope is 0. And think about it, if I have a slope of 0, the line looks like this. So this would be a line, we won't call it M, we'll call it beta sub 1. So if beta sub 1 is equal to 0, I have a horizontal line. Well, for this x value, I'm going to get this value for y. But for this x value, I get the exact same value for y. It doesn't change. So if the slope's 0, all x's are going to give me the same y. It's not going to help me make a good prediction because it's always going to give me the exact same number. Okay, so that's the theory behind it. So my null hypothesis is that the slope beta sub 1 is equal to 0. So regression not useful. The alternative, of course, it's not a very good alternative. Let's start that one over. The alternative hypothesis, of course, is that beta sub 1 is not equal to 0. Might be positive, might be negative. Positive, remember, positive correlation, X and Y go in the same direction, or negative correlation, they go in opposite directions. So that would mean regression is useful. So not useful up there, is useful down here. All right, so there's our setup, and we're going to do it the same way we always do. We're going to go in, we're going to find the p-value, we're going to compare it to the significance level, and we're just going to go from there. Okay, so let's go ahead and do that, and we're just going to jump right in. So all I've got from here is we're going to go ahead and do a problem out of the homework to get an idea how this works. Now, here's the good news. There's only 3 problems in the whole chapter 15 homework. So we're going to do one of them right now. Hopefully we'll be able to recreate that real quickly. 2 of the 3 problems have to do, they're just hypothesis tests. So anyway, let's jump in. We're going to do one of those problems. So let me jump over to, you don't need that up. Let's jump over to the problems, and we will go straight into homework and exams, chapter 15. And I think I'm in the teacher view. So let's get out of the teacher view. You don't have that access. So we'll go down to 15, go into the homework, and let's do question 3. As you see, there's not many problems. Okay, so let's go ahead and do this. We're going to see how it works. Now, here's the good news. To do this by hand is very difficult. In fact, notice they give me X and Y values down here, and then they give me all this other stuff. What they're doing is they're doing some of the calculations for us to make the computations much easier. We don't care about any of that because StatCrunch is going to do all the computations for us. So we don't even have to worry about it. But I will tell you, here's one thing that I'm going to look at. Let's read the problem and then I'll talk about it. It says an instructor at Arizona State University asked a random sample of 6 students to record their study times in a beginning calculus course. She then made a table for total hours studied X over 2 weeks and the test score Y at the end of the 2 weeks. The results are shown in the accompanying table. Presuming that the assumptions for regression inferences are met, decide at the specified significance level whether the data provides sufficient evidence to conclude that the predictor variable is useful in predicting the response variable. Now, we haven't talked about these prior, but let me tell you this. The predictor variable, that's X, is used to predict the response variable, that's Y. That's not a very good Y, but it is Y. So the response variable is Y. We usually call this one the independent variable, and Y the dependent variable. But there's other terms for them, so they use some of them there. Okay, I'm going to actually erase all that because we don't need that up there. Oops. Okay. That's okay. Now, it says, again, the question being, the predictor variable is useful in predicting the response variable. In other words, the way I would word this, let's change my pen color to black, is study time. Remember, that was my X. A good predictor of exam score. That was Y. Okay, so that's the idea behind this. And notice they only give us 6 students because the calculations take so much time if we're doing it by hand. Prior in the last chapter, we looked at, hey, we can look at R squared, the coefficient of determination, to see how much change there is in the score based on the study time. And we looked at R, the linear correlation coefficient, to see how close these points fall to a line. So we looked at each of those. But what we always need to do, if we're going to do regression, we should look at the scatter plot to make sure regression even makes sense. And so when we get our answer, we think that it coincides with what we saw in the picture. So let's go ahead and real quickly, I'm going to go over here. I'm going to click here to open up the data. So we'll open it up in StatCrunch. And what I want to do is I want to do just a quick scatter plot of the data. So let me clear that off. Okay, so I'm going to do a scatter plot. So I'm going to go graph, scatter plot. The X variable is time. The Y variable is score. And I just compute, and it's going to give me the graph. And so we see, hey, it looks like as time gets further, as time increases, test score goes down. And that may be counterintuitive. And let me give you a quick explanation of that. It's not study time for a specific student. It doesn't mean if you study more, you'll do less. So don't think, hey, I've seen the data, I'm going to study less. That's not what it means. What it means is typically in math classes, remember this was a calculus class they were talking about, the students that get it usually get it pretty quickly. A lot of the students that this makes a lot of sense to them, they're really good at math, they don't have to study a lot, they still score really high. But the students that are really having trouble understanding, they're the ones that are more apt to spend more time studying to try to understand it better. And they may not get to the level of somebody that really just got it real quickly. And so what oftentimes happens, what this is showing, the students that really need to study a lot because it's a more difficult subject for them might not score as high. But I guarantee you, you study more, you'll do better. So this isn't on an individual case. This is on a everybody in the class case. Okay, so anyway, but it looks like if I were to draw a line here, the line would clearly look something like this. I didn't draw a line, I tried to. It looks something like this. It'd be straighter than that, obviously, but it's definitely going down. And we'll talk about that when we do this test. Okay, so anyway, I'm going to clear that off. But we do see that it looks linear. So doing this hypothesis test makes sense. Okay, so what I'm going to do is I'm going to actually do the hypothesis test. So let's set it up. So I'm going to start off, I'm going to say, okay, let's do the null hypothesis. So I've got H sub 0 is that the slope of the population regression line is 0. So beta sub 1 is 0. The alternative is that it's not equal to 0. Beta sub 1 is not equal to 0. Remember, this means not useful, and this means useful. Okay, so now we're going to go through, and what I want to find the p-value. We're going to figure out what that is, and then we'll compare it to whatever they give us for alpha. All right, so we'll get that, and we'll compare it to whatever my value of alpha is. And in fact, we'll compare it to see if it's less than or equal to alpha. So I'll leave that there for now. We'll plug things in. But now I'm going to do the test. Well, again, the test is just as easy as the graph was. I go up here to stat instead of graph. Probably shouldn't have written over all that stuff. But what I'm doing, I'm going down, you see it right under p-value, regression, simple linear, just like the way I found R and R squared. We'll see those again. So we go simple linear. The X variable again is time. The y variable again is score. I'm doing a hypothesis test. Let's see, if I move this over, we'll be able to see that a little bit better. I'm performing a hypothesis test. The intercept, they're assuming is 0. We don't care about the intercept, so that we're not worried about. What we care about is the slope. So the null hypothesis says the slope is 0. Yeah, that's what we said. Versus not equal to 0. We could change that. We're never going to change it. We just want to see if it's useful. We don't care if it's just specifically a downward slope or an upward slope. We just want to know if it's not 0. Because if it's not 0, it's useful. And again, that's all I do. It's already checked for us. I just click on compute. And a couple things. Notice the R value, the correlation coefficient, was negative. It should be negative because the slope of that line was going down. And it's 0.69. So the points are kind of close to a line, but not too much. But the R squared, notice the R squared, 0.486 if we round that off. So 48.6 of the change in score is explained by the time studied. But it's negative. Study more, score less. So anyway, but for our hypothesis test, what I care about is the p-value. Again, we don't care about the intercept, just the slope. So let's look down here at the slope. Didn't mean to highlight all that stuff. Let's look down here at the slope. We make this bigger. There, it's bigger. Still have all that stuff right in the way. Well, that's kind of unfortunate. But here's the slope, the p-value over here. Well, here's t. We'll write that down. So let's go t equals, what do we have? They usually go to, well, let's go to a bunch of decimal places. 1.94. They usually go to 3. Let me go to 4, 3, 2. That's probably going to be to 2 decimal places. So we've got plenty. The p-value they gave us as 0.1239. All right. So that's all I need. So we're looking nice. Remember, if I wanted the regression equation, it's here too. Here's the regression equation. Y equals 92.467 minus 0.60 times x. That time is just they put in, because we called it time x. That's how we labeled that first column. So that's why it's in there. Now, I will tell you, every time x increases by 1, the score goes down by 0.6. So if somebody studied, say, 10 more hours than somebody else, their score would go down about 6% more than somebody else. And again, their score is not going down. It's just saying, hey, when somebody scored this much, what would we predict they're going to score on the test? Okay, so we've got that. We're ready to go ahead and finish this problem. So let's get out of StatCrunch, and it'll keep all my stuff here, which will be nice. And go back to the problem, which is here. Okay, so I've got, if I move, I can't move that stuff up. Okay, but let's answer the questions. It said, what are the hypotheses for the test? Well, beta sub 1 is 0 versus beta sub 1 is not equal to 0. Let's see, not the first one. Beta, it's B. The null hypothesis beta sub 1 is equal to 0, and the alternative is beta sub 1 is not equal to 0. So we check that one, get the right answer. Go on to the next part. It says, what's the t statistic? Rounded to 2 decimal places. Well, I already wrote that down, negative 1.94. So let me pull up my keyboard. Negative 1.94. And we'll check that one. Hey, we got that one right also. What's the p-value? Oh, the p-value, 0.1239. They said go to 3 decimal places, so 0.124. Let's put that here. 0, oops. 0. All right, I need more room. Eraser. That's what I got for being so overzealous. 0.124. We're checking to see if it's less than or equal to, they gave us here an alpha value of 0.10. That's alpha, that's my significance level. We'll go back to that in a second. Let's put in the p-value. So the p-value, open up my keyboard again, 0.124. 0.124. Got the right answer there. All right. Now, before we go to the answer, let's answer this ourselves. Again, I always recommend you do the hypothesis test yourself. And I would have done the whole thing start to finish. I just didn't have any clean room. Obviously, if I went off to the right, I probably would have had enough room because there's stuff over there that's some nice blank space. But let's go back to my p-value. So I have a p-value of 0.124. And I say, oh, is that less than or equal to 0.10? No, it's absolutely not. Notice this is 12.4% and this is 10%. That's not less. That's not less, so I do not reject the null hypothesis. And if I can't reject the null hypothesis, it might mean that beta sub 1 is equal to 0, meaning the regression equation is not useful. So do not reject the null hypothesis. And I have to say no. The regression equation is not useful in using our study. To predict test scores. All right, so let's look at what they give us. So let's see, A says reject the null hypothesis. We know that can't be it because we didn't reject. B, do not reject null hypothesis. So far, so good. The data provides sufficient evidence to conclude that our study is useful. No, that's the conclusion if we reject. So it must be C. I mean, it must, C says reject. Must be D, do not reject. The data do not provide sufficient evidence to conclude that our study is useful in predicting test scores. So it's got to be D. And bam, we check our answer and it says you are so smart. Let's erase all this so we see that it says, hey, that was fantastic. All right, so anyway, work on this, not too bad. It's hypothesis tests. We've done a ton of hypothesis tests so far. We have one chapter left. We're gonna go into chapter 16 next time, and chapter 16 is another hypothesis test. It's called an ANOVA test. So we'll talk about that next time. But good job. We finished this. We did our homework. We're ready to go on, ready to get into our very last chapter of the semester. So great job. Keep up the good work, and we will talk more later. All right. Thank you much. You have a great day.